Hi everyone, I'm Aditya, and today I'll be talking about our work on discovering axiomatizations automatically using logic learning. Now, this is actually a problem of great interest to all of us, right? Because axioms are foundational to deductive reasoning. And we often work with a class of structures in our mind, let's say groups or arrays, the theory of integers with addition, even heaps. And we write down properties about them. And we develop a vocabulary in this process, and we use those properties to reason abstractly about these structures. And that's how we get things like, Pressburger arithmetic or the theory of arrays with updates and things like that. We also use this knowledge to build algorithms that manipulate arrays or abstract data types or algebraic data types. And we're able to reason that these algorithms are correct because we know intuitively what they manipulate about these structures in terms of the abstract properties that we wrote down. But this is actually a very hard job, you see, because if you've tried to create an axiomatization, if you've even tried to learn an axiomatization, you've certainly appreciated the amount of ingenuity that goes into creating one. And your marvel wouldn't be misplaced, right? Because developing axiomatizations requires many years of hard work by many expert logicians. So why is that the case? Let's reflect on that task for a moment. Coming up with an axiomatization essentially involves two kinds of things. One, conjecturing interesting properties. And two, being able to reason about those properties in terms of, I don't know whether they're correct, whether they are sufficiently descriptive, and so on. And if indeed we accept that synthesizing axiomatizations involves these two kinds of thinking, it is also true that the last few years have seen a tremendous amount of improvement in program synthesis or expression synthesis, and also in automated reasoning in terms of SMT solvers or even automated theorem provers. And so, knowing that there have been improvements and knowing that these two are the kinds of things that are required to synthesize axiomatizations, in this work, we asked the perhaps fantastical, even audacious question, can computers help us find axiomatizations? And that's what I'm going to talk to you about for the rest of this talk. Let's look at some kind of working definition of an axiomatization so we're all on the same page. We have a base class of structures B and a subclass of structures T that we want to axiomatize. T is called the target class. And then an axiomatization A for axioms, is a set of properties, phi 1 through phi n, such that two things are true. One, every phi I is valid over T. That's the basic soundness criterion. You want your axioms to be true about your target class. And two, for any property that is valid over the target class, it is logically entailed by your axioms. And what this means is that your axioms actually capture all the properties of the target class. This is called a complete axiomatization. But there's one crucial element here that you're missing, which is essentially that these properties are stated in a logic. What's really happening is that there's a class that we have in our minds whose dynamics we know very well, very minutely. And we want to describe them using a vocabulary that has the right set of abstractions for our applications. Let's think about the motion of objects in three-dimensional space. It actually involves very complicated interaction between particles, even at the level of electrons. But at the level of everyday objects, we don't talk about things in particle physics, right? We talk about it with the vocabulary of speed, distance, acceleration, and so on. And we instead characterize the motion of objects in space, say, using Newton's laws of motions. And so that's the idea. So let's look at the picture of axiomatization, incorporating the fact that there is a specific language in which we're looking at axioms. Consider a logic L in the abstract sense. And what I mean by this is that you're given a syntax and a semantics. The syntax is given by a set of formulas gamma. And you also have a set of structures, a class of structures B over which this logic operates. And then you have the satisfaction relation double turnstile that tells you when a formula satisfies a model. The target class is a particular subset of this base class, which is all models of the logic. And then we can state in familiar formal notation what it means for an axiomatization to be sound and complete, which we saw in the earlier slide. So for example, for soundness, you'd say every formula phi I, see now these properties are formulae in this logic, is valid with respect to the target class T. And that's written using that entailment relation. We can visualize this using the picture on the right. We have the base and target classes B and T, and we also have axioms phi 1, phi 2, and phi 3. Each axiom phi I essentially culls out a subclass of all models, essentially those models where that particular axiom is true. So what happens is when we're discovering an axiomatization, the addition of each new axiom makes the class of models captured smaller and smaller. And so that's the idea, right? But now what this means is that the ideal scenario, what we would want to call a complete axiomatization, would actually be something that precisely captures T. But there's actually a small subtlety here. You could think of it this way for a working definition. But a complete axiomatization could in fact include models that are not in T, but that are logically indistinguishable from T using the logic L. We discussed this more in detail in the paper, and I encourage all of you to check it out. So we can now look at the examples that I mentioned earlier in this setting. We can have the target class to be groups. The logic L could be equations with a binary operator for multiplication and a constant for identity. And then the axioms would be the usual group axioms. Another example is where T contains just the one model of natural numbers. L is first order logic with a binary operator and the constant 0, 1, and A consists of Presburg arithmetic axioms. And in this case, Presburg arithmetic is actually complete in this sense. Note that this is a model theoretic view of axiomatization, in the sense that an axiomatization simply characterizes T as a subclass of B by culling out subclasses of B using formulas. And the definition of an axiomatization is actually independent of any proof system or a notion of derivability from axioms. However, note that if you indeed had a proof system that was strongly complete, then a completeness in our setting is the same as what you would think of as a complete proof system. And what I mean by that is that if you had a proof system that was strong enough, using a complete axiomatization, you could in fact derive all valid properties about the target class. We also discussed this nuance in the paper, and you can read it at a leisurely pace. All right, let's look at the problem statement. It can be stated very simply as given L, the logic, and T, the target class, find an axiomatization of T. And of course, in practice, we want to find axioms that capture the target class as precisely as possible, where a precise axiomatization is one whose class of captured models, in the sense of the slide that we saw earlier, is smaller. Before we go on to how we solve this, let's actually reflect for a moment on this problem statement and take some kind of inspiration from how we as humans would solve it. Let's say we have a target class T in mind, say familiar lists of integers defined as an algebraic data type. And you want to axiomatize this using the language of constructors and destructors. Let's say that's the problem statement. First, you would just try to come up with properties that you feel to be true about the target class, right? For example, you would say, for all x and y, if the destructors are equal, then x and y are equal. So you'd say if head of x is equal to head of y and tail of x is equal to tail of y, then x and y are equal. And then you would test this hypothesis, either trying to test it using examples or come up with some kind of meta argument as to why this might be the case. And once you're happy with your axiom, you'd ask yourself, are we done now? And this is usually pretty hard because what you have to reason is, does every property of lists with integers follow from the axioms that I have? And that's when you'd really be done. Now, if you're not done, you'd ask, what else can I say about my target class? And I emphasize the else part here because in practice, at least going in, you're trying to discover axioms that aren't already entailed by what you already know. Of course, this might also be hard because you might think you've discovered something new, but it might follow from what you've already discovered. Now, let's say you imagine you came up with for all x, tail of x is not equal to x as the next suggestion. Now, when you think about this is true, you might say, oh, for nil, I actually don't know whether I want tail of nil to be equal to nil. So you can say, okay, for now, what I'll do is I'll say that the axiom is for all x, when x is not equal to nil, then tail of x is not equal to x. And the next time you come up with a proposal, you would know to check it against nil because that's a corner case that has tripped you up in the past. And so this is essentially the workflow that I'm going to talk about. So in this work, we introduce a framework called learning-based axiom synthesis, or LAS, to solve the axiom synthesis problem. It requires you to build certain components. So I'll talk about the components first before presenting the algorithm. The first component is a soundness checker. Given a candidate formula, it checks whether that formula is indeed an axiom, which is to say that it checks whether that formula is valid over the target class T. Next, if a proposal is not valid, the counterexample generator generates a counterexample. This is a model in the target class that the axiom does not satisfy. So next time, you're saying next time you come up with a formula, make sure your axiom works on at least this model. The next component is an independence checker. This is to check whether a sound axiom you proposed follows from all the previous axioms you know or is truly new. And we can formally state this as an entailment in the logic. The last component is the logic learner, which, given a bunch of examples of models in the target class, comes up with a formula that satisfies all of them. So there are some cool things here. As I mentioned, the target class may only be in your mind. so might be the base class. So how do we specify them formally in a problem statement ready for automation? It turns out that you can think of these components as actually being an operational formal definition of your class. The soundness checker implicitly specifies the target class T, the independence checker implicitly specifies the base class B, and so on. And so the LAS framework actually serves as an operational definition of the problem statement. You may have also noticed that I've not mentioned a component that checks whether the axioms are good enough, so something like a completeness checker. Since checking completeness is hard enough manually, let alone automated, we keep completeness checking as an optional component and only use it if you can actually build one. It's not essential to have one to use LAS. And I encourage you to look at the paper for discussions about completeness and checking it automatically. Great. Now that we have the components, here is the LAS algorithm that uses the components that we talked about. I'll only be discussing here the common case for simplicity, just to build some kind of intuition. The algorithm starts with the logic learner proposing a candidate formula. We first ask the soundness checker whether it is indeed an axiom. If it is, we ask the independence checker if the axiom is not redundant given previously discovered axioms. And if it is, we declare that an axiom has indeed been found. Yay. If the proposed formula is not sound, we ask the counterexample generator for a model that shows that this formula is not an axiom. And we add this model to a set of counterexamples that we maintain and ask the learner to give us another candidate. Now, if the independence check fails, then we simply say that we want to avoid this formula. To do this, we maintain a set of formulas to avoid. The logic learner then always proposes a candidate that satisfies all the counterexamples that is also not any of the formulas in the avoided set. That's really what the logic learner does. We repeat this procedure until we're satisfied. The termination, of course, depends on the domain, and there are many choices here. You could run it until timeout. You could run it until a completeness checker says, yes, you're done. Or you can even choose to do something empirical, like have a hidden set of theorems that you want to be entailed or derivable. Note the really cool thing here, which is that the learner only gets fed counterexamples. It doesn't know anything about your target class. All it knows is the logic and how to evaluate formulas on models in your logic. I'm really calling them counterexamples to evoke a familiar notion in your mind, but they are just examples of the class that you're trying to axiomatize. The LAS framework actually cleverly separates the various capabilities required for axiom synthesis into components that can in fact be implemented in a practical setting, even when you don't know the target class articulately. So we're going to look at precisely this next. I'm going to put my money where my mouth is, and I'm going to show you what it looks like to operationalize LAS for a particular domain. So let's look at modal logic. We already, Let's first look at the syntax and semantics of modal logic. Modal logic talks about these directed graphs called frames. You have an example of a frame shown here. The nodes are called worlds, and the directed edge R is called the accessibility relation. The syntax is also shown here. It's similar to propositional logic, except the two new operators. Box phi says that every accessible world satisfies phi, and diamond phi says some accessible world satisfies phi. So for example, in the model here, let's say that a world satisfies the proposition golden if it's gold colored. So if you ask in this model, starting from the world Y, is box diamond golden true? It is, because box from Y takes you to all possible worlds, which is just W. And diamond on W asks you to choose one, and you can choose W itself, and that is in fact golden. But if you say whether this formula is true starting from W, then this is not true, because box diamond invariably takes you to Y, and Y isn't golden colored. Let's now look at what the axiomatization problem is. We already know that the logic L is modal logic, and the base class B is the class of all possible frames. For the target class, let's take the example of what are called serial frames. A serial frame is one for which in every world, there is a world accessible from it. So the frame on the left is a serial frame, but the frame on the right is not. The target class here is not just in my mind, but is in fact precisely defined by the first order formula that you see on the slide. The objective then is to try and describe such frames using modal logic itself. Now, you can think about it first if you've understood enough of modal logic from my previous slide. But otherwise, let me tell you what the answer is. This class is actually well studied in the literature, and it turns out that the formula box alpha implies diamond alpha completely axiomatizes serial frames. This is a schema, and what I really mean is that for serial frames, and only for serial frames, all formulas of the form box alpha implies diamond alpha for concrete values of alpha are satisfied. We can quickly look at why this is. The hard part of the argument is to essentially show that the completeness. So assume that the axiom is actually not true. So you have a world where every accessible world satisfies some property, but you can't produce even one concrete world that does. How is this possible? This can only happen when there are in fact no accessible worlds. And so when you say every accessible world, you're saying that it's vacuously true. So if this axiom isn't true, there is in fact a world with no successors from it, with no accessible worlds from it. And so that frame isn't serial. That is the essence of the argument. This problem is studied in the area of correspondence theory, which studies a large number of these frame classes like serial frames, Euclidean frames, and famously reflexive transitive frames that are defined using first-order logic formulas, and it tries to axiomatize them using modal logic formulas. Expert logicians have worked on this, and you can in fact refer to our paper for citations to the literature about this problem. Great. I'm going to briefly show you how we applied the LAS framework to modal axiomatizations. So remember, we're given a first order characterization of a class of frames, like serial frames, and we want to find the modal axioms that capture this class. For soundness, we're given a modal logic schema. We first replace schema variables by propositions, and it turns out that that's sufficient. So now we just have a normal modal logic formula. We convert this to first order logic by changing the box and diamond to universal and existential quantifiers. And then asking if it's a valid axiom for a class just involves asking whether the class description, which is already in first order logic, implies our translated formula. And we simply use off the shelf first order logic solvers for this. Generating counterexamples turns out to be not so simple because it's possible for frames to have infinitely many worlds, and you may only have counterexamples of that sort. In our experiments, we just look at frames of a bounded size as counterexamples, gradually increasing the size bound. Independence checking is super complicated because the axioms are schemas again. This essentially brings forth a sort of second order quantification. So in our experiments, we relax the second order quantification by only checking independence on frames of bounded size. So what we're really asking is, among frames of bounded size, is my new axiom truly new, or does it follow from previously known axioms? The logic learner is implemented by a very careful process. First, we write a grammar of modal logic formulas of bounded height, and we encode the choice of the formula in the grammar using Boolean variables. Right? And then we write what it means for a concrete formula in the grammar to satisfy a counterexample model as an SMT constraint. And we do constraint-based synthesis. This is a fairly standard bag of tricks. The subtlety actually is in how we give the counterexamples in a way that can be encoded for constraint-based synthesis. And I once again point you to the paper. For this detail is actually pretty interesting. The last thing is completeness. It also suffers from the issue of second order quantification, but more importantly, to our knowledge, there are actually no solvers that can check completeness for modal logic. So what we do is in this work, we develop a novel completeness checker that generalizes the intuition from manual proofs of completeness that are done in modal logic literature. And you can check out this solver in the paper. As you can see, while the LAS framework tells you what to build, actually building this framework for each domain is something that isn't trivial. Let's look at some results. We apply the LAS framework to 17 commonly studied classes of frames. They have first order descriptions that are shown here on the left. Some of the classes are combinations of the basic classes shown here. You can see the famously studied classes of frames like reflexive transitive frames over here, what many call S4. Our tool is effective in this domain, synthesizing complete axiomatizations for all 17 logics. Among these, the new completeness checker we developed in this work is automatically able to verify completeness for 14 out of the 17 logics. It is our conjecture that this tool is incredibly fast, less than 1 minute, because we have an ideal type of counterexample for modal logic, namely bounded sized frames. And you can actually see that many axiomatizations discovered by our tool correspond closely with human discovered ones found in the literature, modulo some small rewrites. So for example, for reflexive frames, the human discovered axiom is box alpha implies alpha. Our tool finds not alpha or diamond alpha, which if you convert to an implication, you'll actually see that it's just the contrapositive of the human discovered axiom. And because box becomes diamond under negation and diamond becomes box under negation. More interestingly, for serial frames, the tool finds the axiom diamond true, whereas the human discovered axiom is box alpha implies diamond alpha. The tool's axiom is correct and is in fact complete, which we can verify automatically, but it's possible that there are aesthetic reasons why humans have not found this axiom, maybe because it's very short, or maybe because it just has the formula true. It's quite opaque actually, because it's not immediately obvious that diamond true is the same as box alpha implies diamond alpha. And in fact, this was not obvious to us. It was pretty surprising. There are other interesting patterns of this sort, and I point you to the paper for a broader discussion of our experiments on modal logic. Now, I want to turn to the second domain that we study in this paper, which is languages under a Kleene algebra. This is actually something we're all familiar with in the PL community, so I'm only going to discuss the syntax and semantics very quickly. The target class is, of course, models of languages over a certain alphabet. The logic is equations over the familiar language of union, concatenation, and Kleene iteration. There are two constants. 0 is the empty language, and 1 is the singleton language containing just the empty string. This is the usual Kleene algebra semantics for languages. Now, the base class is arbitrary first order models, which means the operators can have any interpretation. This is actually quite different from modal logics because what we're saying here is that we have a model in mind whose operators have some semantics that we know or that we might be able to code up, but we're trying to axiomatically describe this class by relating the operators. So, and this is in fact very different from the modal logic example where the base class is all frames. The implementation of components for the framework is also fairly different. Soundness reduces to checking equivalence of regular expressions. Count examples are a little more complicated because all models are infinite. So even if you have one letter in your alphabet, you have infinitely many strings, which means you have infinitely many languages. So what we do is we just produce a partial model that explores the true infinite model on certain finite parts. The idea is that the parts that we explore are good enough to inform the axiom synthesis in the following rounds. Independence checking is simply first order validity because our base class is arbitrary first order models. We use off the shelf solvers for checking first order validity. The learner is actually pretty interesting and is in fact very similar to the one that we use for modal logic. We talk about the general principle behind a logic learner based on constraint based synthesis in the paper. Finally, completeness checking is not applicable here because it is known that equational axioms alone are insufficient to characterize Kleene algebras. A famous work by Kozin completely axiomatizes Kleene algebras using both equational axioms and non-equational axioms. But since our logic is just equational axioms, in this case, we simply run the tool until it exhausts the search space. We made the search space large enough to include the reference axioms from Kozin's work. That's how we chose when to stop. Let's look at the results. We discover 15 axioms in the search space with the same size parameters as Kozin's axioms. They cover all known equational axioms from Kozin's axiomatization. But in fact, we discover 5 new axioms that are more powerful than the equational subset of Kozin's axioms. That's pretty cool because if you have a rewriting system that only uses equations, you can use the more powerful axioms that we discovered that were discovered by in our work. Since Kozin's axiomatization is incomplete, is in fact complete, they are, of course, not more powerful than the whole axiomatization. Our axioms are just more powerful than the equational subset of Kozin's axioms. And that's about it. So in summary, I've presented to you our work on learning-based axiom synthesis that breaks ground on the very interesting, very challenging artificial intelligence problem of synthesizing axiomatizations. We've developed a bunch of techniques and we've explored the search space, the problem space enough to discuss the amount of variety and the amount of ingenuity that needs to go into building an automated system. Once again, I'd encourage you to check out the paper for all the details. It's very interesting. I just want to very quickly talk about what future work we have in mind over here, because so far I've only shown you things that humans already know how to axiomatize. The first application is perhaps domains that might be too tedious for humans to axiomatize. For example, CPU instruction sets have intricate semantics and they change very frequently and they vary for every single architecture. So we can axiomatize them and remove the burden from the human. And it might also be useful for other things, like, for example, there's some related work that you can find in our paper that tries to find constant time implementations to prevent timing attacks. So instead of saying sub a comma b for writing a minus b, you might write add a comma unary minus of b. And you can find things like this in the paper. The other application is to perhaps learn axioms for things like metamorphic tests where the actual functional specification is too difficult, but you can in fact discover axiomatically what this function should be. You can learn to characterize a set of equivalences of programs, which recent work has used to find applications for database programs. And there, of course, there are applications that are much further out there to, for example, try and discover axioms of an unknown environment. So you want to try and discover the underlying physics of what you're seeing by just observation. And there's very interesting work in the machine learning community that are looking at axiomatizations that are not even previously axiomatized by humans. And so this would also be something where we can provide a technique that is, very strongly rooted in techniques that we've developed in the synthesis community over the last few years, and offer this as another toolkit towards this very important problem. Thanks a lot.
based on the properties that you have, that the logic is minimal.
Could you elaborate on what you mean by the logic is minimal?
It said that it doesn't, it has minimal set of axioms that you require to prove the property.
I see. So let's say you have a hidden set of properties and you've discovered some axioms, and then you want to establish that the axiom set is in fact minimal. Right. So actually, you could read the related work section of our paper. This is very cool because there's actually a long tradition of people going back to Tarski for people who are trying to find short and simple axioms for things like groups and monoids, various kinds of classes of group actions and so on. They actually made quite a bit of progress by just using enumeration because the axioms were terribly short and simple. But let's say your axioms were more complicated, your search space was pretty large. Once you find an axiomatization using our technique, you might be able to then down search for a more minimal set. So you can, I don't know if you can search for any minimal set that's smaller than that, but you can look for minimal sets that are in some structured way. So, the easiest example you can think of is, can I knock out even one axiom and, will this already be okay? And that kind of check we already actually do in our paper. I didn't talk about it in the experiments for lack of time, but we already do check that our axioms are minimal, at least the ones that are reported in the paper. And there may be other ways of doing this. In fact, lots of works in synthesis try to just knock out arbitrary expressions from the middle of your equation and then see if that's already true. And you might be able to do a bunch of like fuzzing techniques like this.
Hi, really interesting. Okay.
Oh, hi.
I have one question about a specific application. Have you done any experiments trying, let's say you have a group you have some information about, if you don't have like relations to describe that group. Have you tried using this to try to learn like a presentation of a group that you might not know how to present?
So you have a group presentation.
Well, you don't have the presentation yet, you just have the group and
you just have something in your mind, and have you thought about, so in some sense, Kleene algebras are like that, right? I mean, so just for the sake of just answering your question, let me give you the easiest answer, which is that Kleene algebras are already like that. We only had it in our mind, and we weren't basing off of axioms when we, reduced it to equivalence of regular expressions and so on. So that's already an example. But do you mean that you have some data given to you, like actual examples, or do you mean that the examples in your mind? Because the data-driven setting is a very different thing. It's certainly a kind of direction where this work can go, but that's not the problem that we study. We assume that you already know what you're talking about.
Right, so I have specific examples in mind that might give it too long to go into. Just to put it, I'm coming from the side of like quantum computing, and one of the interesting questions is sometimes you have these groups, and you actually reason about them equationally, and sometimes it's left to find these relations.
Right. So, yeah, I think perhaps it's best if we take this question offline. We actually have a toy example in the beginning of our paper where we try to do this for equivalence relations. And so equivalence relation, there's really only like a couple of definitions going on, and we don't use a specific presentation. We try to come up with the reflexivity, symmetry, and transitivity by having the thing in our mind that for each element you can pick a representative element, and that's all you know about it, right? There's no presentation going on. But checking completeness and things like that turns out to be quite hard if you only have the stuff in your mind, because you really have to imagine what all the properties are about this class, and that's not easy to do.
Okay.